So we left off having looked at the Shannon information content, which tells us the surprise that we encounter when we read the one realization of our variable x, lowercase x for the realization, uppercase X for the variable. So the Shannon information content, as I say, is associated with one realization of our variable. We might want to think about what the average surprise is that we encounter across the ensemble of realizations for that variable. That will give us a measure related to the variable itself rather than related to each individual realization or observation. This is where the Shannon entropy comes in. It's an expectation value or an average over the Shannon information content for each realization. It's the average surprise that we see for realizations of the variable x. We can see this in the equation here. We can recognize the Shannon information content for realization little x here, and then we have the sum over all possible realizations normalizing by the probability. So this is doing an averaging, and that's indicated down here where we write the Shannon entropy as the expectation value over the Shannon information content of each realization x of the variable bx. So let me emphasize that again. The Shannon entropy is simply the expectation value of the Shannon information content over all realizations. It is greater than or equal to 0. So as we saw for Shannon information content, we can't be negatively surprised. In the same way, we can't have negative Shannon entropy. So as an average over the variable, the Shannon entropy measures our uncertainty, our expected uncertainty of the answer to our question. So whatever question our variable x is answering, the Shannon entropy tells us our uncertainty before we read the answer or see the realization. Okay, it's an average, it's our average uncertainty. The Shannon information content tells us the surprise or the uncertainty reduction we get when we read that realization. We take the convention in the mathematics here that for any symbol with a 0 probability, it doesn't contribute to the Shannon entropy because we simply never see that symbol. So mathematically, we take this approximation that p log p goes to 0 in the limit as the probability itself goes to 0, and that makes sure that that realization does not contribute to the Shannon entropy on average. We can look at some simple examples here. If there is one symbol that has a probability of 1 of occurring, that means we only ever see that symbol, then obviously we have no uncertainty in what we're going to read from the variable. So therefore the Shannon entropy in this case is exactly equal to 0. As another example, let's say we have a binary variable x and our values, our realizations are equiprobable, 50-50, then in this case we have a Shannon entropy of 1 bit. Okay, so classically here it takes 1 bit for us to, we have 1 bit of uncertainty if we don't know whether we're going to get a yes or a no, a male or a female, or any other 50-50 random draw. Okay, so it's the classic interpretation of 1 bit. Now let's say we have a set of symbols where, remember, AX is our symbol alphabet, so let's say for our set of symbols, our symbols are equiprobable. So the probability of each symbol or realization is 1 over the size of our alphabet. Then our Shannon entropy is simply the log of the alphabet size, and of course the Shannon information content for any realization is equal to the same value here. Okay, so it's some simple calculations of the Shannon entropy. There are some other calculations I've given you in exercises. We're going to skip them right now, and we're going to move on. To consider the meaning of entropy. So we can interpret the Shannon entropy and the Shannon information content if we think about trying to encode our random draws x of our variable bx. Now, if we need to encode them, generally we will want to use an optimal compression or encoding scheme. We're assuming that we know the probability of each symbol occurring. If we know that, then the optimal encoding scheme, under the optimal encoding scheme, we will use the Shannon information, the number of bits that the Shannon information content computes for a given symbol little x. We'll use that number of bits to communicate that random draw. And on average, the Shannon entropy tells us the number of bits we need to communicate these realizations on average. Okay, this is a very important interpretation of what the Shannon entropy and the Shannon information content are giving us. They are telling us the number of bits we will use for each symbol and on average to encode these realizations if we need to tell somebody what they were. Okay, so you can think about this very simply. If we're encoding a coin flip, if it's a head or a tail and it's a normal coin, 50-50 random draw, we need 1 bit to encode each outcome, say a 0 for a tail or a 1 for a head. That's simple to understand. What's important here is, remember we talked before about some biased examples. For example, if we thought about men or women walking through a door, if there were many more women, then that was far less surprising, but if there were very few men, then it would be very surprising for a man to walk through the door. Here we can see that very surprising outcomes which have high Shannon information content are the ones that we use a large number of bits for. Very unsurprising events with low Shannon information content we use small numbers of bits for. That's because if they're not surprising, we don't need many bits to communicate them. And that saves us on average. We can then sort of use longer encoding streams to encode our surprising values because they don't occur very often. So we can afford to push some extra code into those infrequent examples to save code on the more frequent examples. And then we save on average. Another way we can look at this is to think about how many, or how few rather, yes or no questions we need to ask on average to determine the value of a variable from the random draw. Okay, the entropy is telling us that, how many yes or no questions we will need on average. For a specific question, the Shannon information content will tell us our surprise at that answer. Okay, for a specific question or a specific value of x. But on average, the entropy is telling us how many yes or no questions we need to ask on average to determine the value of our variable. So we can think about guess who, which we looked at earlier, as a decoding task. What you are doing in asking your partner yes and no questions is effectively decoding the person that they have, and you are trying to do that in the most efficient way possible. Coming back to traditional uses of information theory, as I've said before, it was traditionally used in communications and signal theory. This diagram is a classic schematic of a general communication system where we are encoding an information source and decoding it at the receiver. So here, thinking about traditional uses, we can see that information theory has been used to look at size of zip files, to compress music into MP3s, to encode mobile telecommunications, and so on. And all of these uses gel directly with our interpretation up here of Shannon information content and Shannon entropy regarding encoding schemes and optimal encoding schemes.